We interrupt this regularly scheduled probability to bring you some important messages about orthogonal projections. Orthogonal projections come from linear algebra, and much of what we're going to discuss in this lecture is pretty much basic linear algebra, but believe it or not, it is highly relevant to our current discussion of conditional expectation. If H is any finite-dimensional vector space equipped with an inner product, just think RD with its usual dot product, and if K is any linear subspace, then there is an orthogonal projection mapping from the big space H onto the little space K. This double arrow here means a surjective map. This linear transformation, PK, the orthogonal projection onto K, has the properties that it fixes all of the vectors in the subspace K, and it kills all the vectors that are orthogonal to K. Here the orthogonal complement of K is the set of vectors W such that the dot product of V with W is equal to 0 for all vectors V that are in K. So of course visually we know what this means. We have our subspace of the space K, which in this case is the screen. And we'd like to orthogonally project a vector, say this one, onto K. The way we accomplish that is by looking at the orthogonal complement to K, which in this case is this one-dimensional subspace here, and then we project down along that subspace onto K. So in other words, we take a vector that is parallel to the orthogonal complement to K, and we draw down along that vector, and that gives us our orthogonal projection. The key here was actually to find this vector, V minus the projection onto V, which is orthogonal to K. And that, it turns out, uniquely specifies what the orthogonal projection is. It's the unique vector so that that difference is orthogonal to K. But we'll get to that. Now in the finite dimensional context, or actually even more generally in the context where we're going to work, but not useful to us, there's a kind of formula for this. If you fix any orthonormal basis for the subspace K, then you can write the projection map as the sum over that basis of the inner product of V with the basis vector times each basis vector. And relevant to our later calculations, if the ENs are orthogonal but not necessarily normalized, then we can get this same formula just by normalize them in both places, which means that we'll have to normalize by the length squared of the vector in the basis. We'd like to develop this same idea of orthogonal projection, but not in a finite dimensional vector space, rather in a infinite dimensional Hilbert space, like L2. A Hilbert space, remember, is any complete inner product space. The example that is most relevant to us is L2 of a probability space. It's in fact an abstract theorem that every Hilbert space looks like L2 of some measure space, but not necessarily a probability space. In this case, the inner product is just given by the expected value of the product of the two variables. Since the x and the y are both in L2, their product is in L1, and this makes sense, and as we've seen, this defines an inner product on this space here, and it is a complete inner product. Now, there are two basic linear algebra / geometry facts about inner products that work here as well as any other inner product space that are going to be critical to our calculations, and they are Pythagoras' theorem and the parallelogram law. Pythagoras' theorem says that if x and y are orthogonal, which is defined to mean that their inner product is 0, then the square of the length of the sum of two vectors is the sum of the squares of their lengths. And this is simply because of the definition of the length, which is just the dot product of the vector with itself. So the left-hand side here is x plus y inner product with x plus y. The inner product is bilinear, so linear in each term, which means we can FOIL this out to write it as x dot x plus x dot y plus y dot x plus y dot y. And if x and y are orthogonal, that means that these two terms are both 0, and that, of course, immediately gives us these terms here, proving Pythagoras' theorem, even though I like to eat beans. We also have the parallelogram law, which from classical geometry says that if you draw any parallelogram, like this, with two sets of parallel sides, then if I take the sum of the squares of the four side lengths, that's equal to the sum of the squares of the two diagonal lengths. That is, if I have any two vectors, then the square of the length of the sum plus the square of the length of their difference, which is what these two are, is equal to 2 times the length squared of x plus the length squared of y, which is the sum of the squares of those two plus those two. We can prove this in much the same way. The left-hand side is x plus y dotted with x plus y plus x minus y dotted with x minus y. And if we expand all those terms out, we see that the cross terms cancel, and we're left with 2 copies each of the length squared of x and the length squared of y. So those hold in any inner product space. Now, if our space is a Hilbert space, then we can talk about subspaces of it, but we need to be a little careful, because if we're working in the category of Hilbert spaces, we'd like our subspaces to be Hilbert spaces, but that's not necessarily going to be true. If K is a linear subspace of a Hilbert space, then it is itself an inner product space in the same inner product that's descended from the large space, but it's going to be a Hilbert space if and only if it's complete. And that will be true if and only if K as a subset of H is closed. We can easily construct non-closed linear subspaces. For example, if you take any infinite collection of orthogonal vectors and take their regular span, that is, the set of finite linear combinations of those vectors, that will not be closed in an infinite dimensional Hilbert space. We're going to need closed subspaces so that we stay in the realm of Hilbert spaces. And that leads us to orthogonal projections, which are related to least squares approximation problems in Hilbert spaces. If K is any closed subspace of a Hilbert space, and X is any vector in the big Hilbert space, then we can always find a closest point in K to the vector X. That is, there will always exist a unique point Y that's in the subspace K that has distance from X minimal among all vectors Z that are in K. And actually, this unique minimizer property holds not just for subspaces, but in general for convex subsets, as we'll see in the proof, although I'll restrict it to subspaces in the statement. So here's why this is true. If I take any two vectors, y and z, in the subspace K, I can look at their distance from each other. Now I can write that distance by comparing each of them to the base point x, which is not necessarily in K. And now I can use the parallelogram law, which says that the length squared of the difference of these two vectors plus the length squared of the sum of those two vectors is twice the sum of the squares of the lengths of the two vectors. But if we look at this term on the right-hand side over here, inside there is y plus z minus 2x. And so I can pull out a factor of 2 through the square, writing this instead as 4 times the length squared of y plus z over 2 minus x, quantity squared. Now here's the key observation. This vector here, y plus z over 2, that is in the subspace K. In fact, that would be in the set K so long as K is convex. And so this term is written as the distance squared between an element of K and x, which is the sort of thing we're measuring in this distance. And so rearranging this equation here, we see that y minus z, quantity squared, which is what we started with, plus 4 times that distance between the average of y and z and x squared is equal to twice the sum of the length squareds of those two difference vectors. Now, since y plus z over 2 is in K, it follows that this term here, the length squared of y plus z over 2 minus x squared, is bigger than or equal to the distance from x to the subspace k squared. And so, because of this equality here, and this term being bigger than that, we get that, in fact, the distance between y and z squared plus 4 times the distance from x to the subspace squared is less than or equal to twice the sum of the squares of those two difference vectors. That is the key equation that gives us both existence and uniqueness in the statement of this proposition. For uniqueness, if I had two separate vectors in k, y and z, that both minimize this distance, then I get that the distance squared is equal to the square in both of those cases. But looking at the equation above, that will tell us that the distance between y and z squared plus 4 times that distance is less than or equal to 2 times that distance plus 2 times that distance, all squared. In other words, all of the terms here and here cancel out, and we get that this distance is less than or equal to 0. Of course, that means that the distance, which is a non-negative number, is 0, and therefore y equals z, giving us uniqueness. As for existence, which is the only place where closedness of the subspace is needed, by definition of this distance here, which is this infimum, I can, of course, choose a sequence of yns that come as close as I want to witnessing this distance. In other words, I must be able to find yn in the subspace k, so that the distance squared between x and yn is less than or equal to the infimum plus 1 over n. Well, my claim is that that sequence yn, however I choose it, is now going to be a Cauchy sequence. Because if I take the distance squared between yn and ym, then again, using this inequality here, that distance squared plus 4 times the distance from the point x to k squared will be less than or equal to twice the sum of the squares of the distance between yn and x and ym and x. But we've arranged it so that each of those distances is just a little bit bigger at most than the distance from x to k. So that is, this will be less than or equal to twice the distance squared plus 1 over n plus twice the distance squared plus 1 over m, which is 4 times the distance squared plus 2 times 1 over n plus 1 over m. And so again, we'll get cancellation here, and we see that this is less than or equal to something which tends to 0 as n and m go to infinity, which shows us that yn is a Cauchy sequence in the Hilbert space H. That means, since H is complete, that yn converges to some y in H. But yn is actually in K, the way we've constructed it, and therefore, since K is closed, it follows that y is in K as well. And now if we look at the distance from x to y, well, by the triangle inequality, that's less than or equal to the distance from x to yn plus the distance from yn to y. This goes to 0 as n goes to infinity, and this is less than or equal to the distance from x to k plus 1 over n. And since that's true for every n, we find that indeed this is less than or equal to the lim sup of this side, which is less than or equal to the distance from x to k. But this is, of course, at least as big as the distance from x to k. And so we do find that this y satisfies this equality here, which is what we were hoping to show. Now, it turns out, as you should remember from high school geometry, that that least squares minimizer is also related to the orthogonal projection problem. The unique closest point y in the subspace k to x is also the unique element y of the subspace, which satisfies this equality here. X minus y is orthogonal to k. That is to say, the inner product of x minus y with z is equal to 0 for every vector z in k. Well, let's just prove each of those directions. If y is that closest point, and if we take any z in k, then consider the following auxiliary real-valued function of a real variable t. Alpha of t is the distance squared between x and this affine transformation of y. We move t times z away from the minimizer y. Now, the reason that we are introducing that is that this is a nice function which, by the assumption that y minimizes the distance, has a unique minimizer. This function alpha is minimized at 0, because if we move away t units in any direction z in k, we will be another vector in k, and therefore this distance will be bigger than or equal to the distance from x to y, which minimizes that distance. But we can also expand out what this distance is, again, using the bilinearity of the inner product, and what we will get is the length of x minus y squared minus 2 times t times the dot product of x minus y with z plus the length of z squared times t squared. So the function alpha of t is just a quadratic polynomial with non-negative quadratic term. That means that it opens upward, and it will have a unique minimizer. Well, we already knew it had a unique minimizer, which is precisely at the unique critical point. Since we know that the minimizer occurs at 0, that means that alpha prime at 0 must be 0. But alpha prime at 0 we can compute. It's just minus 2 times the inner product of x minus y with z. And so that shows us that this inner product here is 0 for any such z, which shows that this property holds. For the converse, let's now take y to be a vector which satisfies this condition here. X minus y is orthogonal to k. Well, then if I fix any vector z in k, if I compute the distance between x and z squared, I can now compare that to y. This is the length of x minus y plus y minus z, quantity squared. Now, y minus z is in k because both y and z are in k, and k is a subspace. And these two are orthogonal, therefore, by our assumption. And therefore, we can use Pythagoras' theorem and write this as just the sum of the squares, x minus y squared plus y minus z squared. And of course, this last term here is greater than or equal to 0, being the length squared of some vector, and so this is greater than or equal to x minus y squared. So that shows that for any vector z in k, the distance between x and z is bigger than or equal to the distance between x and y. That is, if y is any such vector satisfying this, then it minimizes the length of the vector from x to k. And we know there's a unique one of those that shows that y is the unique minimizer. And that concludes the proof. What we've learned is that this condition here specifies a unique vector y. That is, for any vector x in any subspace k, there is a unique vector y in the subspace k for which x minus y is perpendicular to that closed subspace k. And that unique vector y is the same one that minimizes this length, the distance from x to k squared. Referring to our intuition in that picture from the first slide, that unique vector y is the orthogonal projection of this vector x into k. And so that gives us most of the following orthogonal projection theorem. Given any Hilbert space H and closed subspace K, there is a unique linear transformation, which we'll call pk, the orthogonal projection onto k, which satisfies the following conditions. pk is a Lipschitz continuous function, which for those of you who know a little bit about functional analysis is just to say that it is a bounded operator with operator norm less than or equal to 1. It fixes all the vectors in k, it kills all the vectors orthogonal to k, and here's the last auxiliary condition. It is self-adjoint with respect to the inner product, and that just means the following. If I take any vectors x and y now in the whole Hilbert space H, and I project x and take the dot product with y, I'll get the same result if I project y and take the dot product with x. I can move the projection across the dot product without changing the value. Moreover, these projections, if I put them together for different subspaces, have a tower property. If I have two closed subspaces, L contained in K contained in H, then if I compose the projections onto K and L in either order, what I just get is the projection onto the smaller subspace. That's orthogonal projection, and it's just defined to be, depending on your taste, either the unique element in the subspace closest to the vector x, or the unique vector y in the subspace for which x minus y is orthogonal to the subspace. So let's prove these properties in turn. We've already shown that there is a unique closest point, and so let's just define our orthogonal projection to be that unique closest point to x that's in the subspace K. We also showed that that unique point is characterized by this property, that that point y, which is now calling the projection of x, minus x is orthogonal to K. So that at least allows us to define this as a function of x. That gives us two of these properties immediately. This one here is clear from this closeness property because if y is already in the subspace, it's pretty clear that y is the closest point to y. The alternate characterization here also gives us this property immediately because if z is orthogonal to k, this property right here tells us that 0 minus z is orthogonal to k, which is exactly what we wanted to show. We also get the surjectivity from here because we can certainly get to every vector in K in the range just by taking that same vector in the domain. Now, we need to show that beyond this being a function, it is a linear transformation. For that, we just use the bilinearity of the inner product. If we take two vectors in the Hilbert space and two real numbers, then for any vector y and k, I can compute this dot product here. If I take the linear combination alpha 1 times the projection of x1 plus alpha 2 times the projection of x2 minus the vector alpha 1 x1 plus alpha 2 x2. I can just combine terms instead and write this on the left-hand side as alpha 1 times p of x1 minus x1 plus alpha 2 times p of x2 minus x2. And now using the bilinearity of the dot product, this is alpha 1 times the projection of x1 minus x1 dot product with k plus alpha 2 times the inner product of p of x2 minus x2 with y. But the projection here is uniquely determined by the condition that this is always 0, and similarly the projection here makes this always 0. And so that shows that this vector here is a vector for which this minus that is orthogonal to all of k. But that uniquely specifies that this vector here is exactly the projection onto k of alpha 1 x1 plus alpha 2 x2. And that shows us that the projection is a linear transformation. So what remains to show is that this linear transformation is Lipschitz continuous with Lipschitz norm at most 1, self-adjoint, and enjoys this tower property when compared to other orthogonal projections. For the Lipschitz condition, that's actually going to follow from Pythagoras' theorem. If we take any vector x in the Hilbert space, we can decompose x as x minus the projection of x plus the projection of x. The point of doing that is that by definition, this is orthogonal to k. And of course, this is in k by definition, and those two are therefore orthogonal to each other. Therefore, the length of x squared, which is the length of the sum of this and this squared, satisfies Pythagoras' theorem, giving us the length of x minus its projection squared plus the length of the projection squared. Now this is a non-negative term, and therefore that sum is greater than or equal to the projection's length squared. So that says that the length of the projection of x is less than or equal to the length of x for every vector x in the Hilbert space. And now linearity of the projection gives us the Lipschitz condition that we want. If I look at the projection of x minus the projection of y length, well, the projection is linear, so that's the same thing as just the projection of x minus y. And now I apply this to the vector x minus y to get that that's less than or equal to x minus y, which is exactly to say that the projection is a lip1 continuous function. Now for the self-adjointness condition, we do something similar. If I project x and then take the dot product with y, I can somewhat mysteriously add this term without changing the value, because this term here is 0. By definition, the projection of y minus y is orthogonal to k, and the projection of x is in k. So these two are orthogonal, and therefore this dot product is 0. But the reason that I've included it there is that I can now combine by the linearity in the second factor. This sum is equal to the projection of x dot product with y plus pk of y minus y, which is just pk of y. And so we see that this apparently asymmetric term here is actually symmetric. We can put the pk in both places, and now just by reversing the roles of x and y and using the symmetry of the inner product, we get that this is also equal to the dot product of x with the projection of y as desired. Finally, for the tower property, if L is a closed subspace of K is a closed subspace of H, well, take any vector x in H, then if I project it into L, I get a vector that's in L, which is therefore also a vector that's in K. So that means that if I take the composition projection onto L followed by projection onto K, well, I'm first doing projection into L, and this vector is in K. And we know that projections fix vectors in the subspace they're projecting onto, and therefore this is equal to the projection onto L of x, which is one of the two statements we wanted to prove. Now, for the reverse, we're actually going to use this self-adjointness condition. If I now take any two vectors, x and y and h, and I look at the projection onto k followed by the projection onto L of x, and take the dot product with y, using the self-adjointness, I can move the projection onto L over to get this, and then I can move the projection onto k over to get this. Now, we just finished showing that PL followed by PK is just the same thing as PL, and so this is the dot product of x with PL of y, and using the self-adjointness one more time, that's the projection onto L of x dot product with y. So what we see is that this vector has the property that if I take its dot product with any y, I get the dot product of this vector with y. In other words, if I take PL pk of x minus PL of x and take its dot product with any vector y in the Hilbert space, that gives me 0. So here's the trick. I can take that y to be that same vector, PL pk of x minus PL of x. And what I get is that the dot product of this vector with itself is 0. But that's the length squared of this vector, which means that this is the 0 vector, which means that the projection onto L is the same as pk followed by PL, which is what we wanted to show. So there are all of the basic properties of orthogonal projections. This lecture didn't have any probability in it at all, or so it would seem. But as we'll see in the next lecture, conditional expectation is nothing other than an example of such an orthogonal projection.